Okay, hello everyone, and welcome to this year's State of Julia talk. Let's first introduce ourselves. My name is Kristoffer Carlsson. I work at Julia Hub. A long time ago, I used to do finite element modeling and material modeling. Then I started helping out a little bit with the new fancy package manager, and one thing led to another, and now I'm standing here presenting State of Julia.
I'm Lilith Hafner. I work on language and tooling with a focus on making Julia more inclusive to new contributors to the language.
And my name's Elliot Saba. I did electrical engineering until I needed something to replace MATLAB, found Julia, fixed a bug in it. Virol was very welcoming, and now here I am.
So first, I want to give a little bit of what is the Julia experience, and this will of course be a very small slice. The Julia experience is very big, but this is a little bit how I feel about it, and what are sort of the core things and the important things. So first, I'm putting some representative code here, and representative code is very hard, but I try to at least include some things that are sort of typical for Julia. So first, we have some useful packages we're loading, like static arrays, fast static-sized arrays. Maybe we want to use units in our code, so we load a unitful package, so we don't add a meter to a second or something. And then maybe we want to find the gravitational constant there, and there's a physical constant package that I can just get that from. And that's also a unitful constant, so if I would take the g there and add it to something, it would error for me. Then we have a struct here, a planet that contains some data. And typical Julia, we have sort of very generic code. So here I'm parameterizing this planet on the floating point type. And I'm also saying that this mass should actually be a mass. It should be a unitful mass. So it's not just a number, it's a mass. And if I do dimensional problems, it's going to error for me. I have some position and a velocity. Maybe I can compute the kinetic energy of a planet then, or the potential energy between two planets. So as you can see here, we have quite a high level of abstractions. We're using units. And there's not that much boilerplate. Sometimes when I go into other projects, I try to find where is the actual code that does the computation. And it could be sometimes a bit hard to find. But I think with Julia, it's pretty easy to find, OK, there's the actual code that is running. And now I could, for example, create the Earth planet here. And I'm using the units here. I'm telling it in kilos and the kilometers where it is, and the velocities in kilometers per second. I'm computing the kinetic energy, and I get that back as a unitful answer here. It's a bit interesting unit here, because I'm using kilometers for the velocity, so I get this in kilograms, kilometers squared per second squared. But I can convert that to gigajoule or something that we're more familiar with. So now we have some code, and I think typically in Julia, we want to do some performance evaluation. We want to see that this thing runs fast. So here I'm trying to load the benchmark tools package, but I hadn't installed it. But then the package manager comes in and is like, oh, I know this package. Do you want me to install it for you? Yes, please. OK, thank you. Now I can use this convenient macro syntax to run the benchmark. And for the potential energy between two celestial bodies here, it was a few nanoseconds. So here we can see we have these zero-cost abstractions in the runtime. I used a bunch of units everywhere. That's going to, at compile time, check that it's going to check that the units are correct. But when I do this at runtime, there's no performance penalty to it. And doing this, I can update my code, and I can benchmark it, and update it, and benchmark it. So it's pretty fast to iterate on some code to make it go faster. And the second part is, if you really want to deep down, you can do this code inspection. And so you can look at this is if you're really interested, but you can look at the LVM code, and you can even go and look at the native code. Here I'm running this on an ARM processor, so there's ARM assembly there. And at least for me, learning this LVM code and assembly, this was using these inspection macros, because in many other languages, it's kind of hard to very easily see, OK, for this function, this is the code that's actually going to run. It's also possible to do some static checks. For example, there's the jet package, and you can do this thing to tell me if I'm doing some common mistakes. Maybe I have type instabilities or something. But here it says no errors detected. OK, that's good. But before we just ran this thing on one thread, but with Julia, we kind of want to use all the compute we have. So if I do this threads.mthreads here, I see I have 8 threads. So if I want to compute the total energy in a system of planets, I can just do it with a simple loop here. I loop over all the planets, compute the kinetic energy, and then I add the potential energy between all the other planets. So this is going to run on a single thread. And it's not much you have to do to make this run on multiple threads. So here I add the threads macro in front of the loop. I just make sure that every thread accumulates into its own variable, and then I do a sum in the end. So now I'm going to define a kind of funny function. It's called a random planet. So I'm just randomizing the mass here. It's going to be maybe it's more like a random asteroid or something, because it's going to be between 0 and 1 kilos. But anyway, it's just to generate some data, a random position, random velocity, and then I can check this, how long time it took when I did the total energy of the planets with the single-threaded, and I can run it with the threaded, and it's quite a bit faster. No, it's not linear speed up here, but it's also this laptop has like different types of cores. It has this fast cores and this more energy-efficient cores, so it's a little bit complicated. There's also more higher-level threading packages that, doing these threads on a loop, it's a little bit low-level maybe, so you can also do this on a more higher level. But let's say I have this very, very strong computer, a cluster or something I want to run Julia. So here's an example. I have this super fast cluster where I have some nice GPUs I want to run my code on. But I log into that cluster, and I do ls, and there's absolutely nothing in there. It's the first time I logged in. And it says, I'm trying to run Julia. It cannot be installed. Please ask your administrator, it says. But I don't think we have to do that. So it's very easy now with Julia App. We can very easily install Julia here locally on this cluster. So I'm just doing this Julia App install command. It installs it. And in the end, I have Julia installed very quickly. So now we have Julia installed on our super fast cluster. But we also have to get our files on there. So I just copy my files from my local hard drive up to the cluster. OK, now they're there. But now in my code, I used a bunch of packages, right? So if I start Julia here on the cluster and I do a status, it shows all these red things that are, the packages are not installed here. But now very easily, it tells us we can just do instantiate. It downloads all the packages we had locally. And it even downloads stuff like the CUDA runtime. So basically, I timed this. It took less than 2 minutes. And everything was installed, and I could start it running. And that was from pretty much scratch there on the remote system. So let's try use these GPUs then. And the fact is, you have to modify your code a little bit to run on the GPU, because running this iterative code is not very well suited for GPUs. So here I kind of rewrote this energy code to be a bit using this broadcast notation. And now let's see if this is useful, or if we spent $10,000 on a very expensive GPU card for nothing. So let's see. I have 64 threads on this remote machine, apparently. I have these 2 GPUs. I create these planets firstly on the host, or on the normal memory, and then I also have it on the GPU. And then let's say I first run it serially. It took some time. Run it with threads. It was quite a lot faster. And now I just ran it on the GPU, and it was even faster. So thanks, we didn't spend all that money for nothing. So to summarize a little bit the Julia experience, we have generic code, the abstract over the floating point type, the dimension. We have a lot of useful packages like units and so on. High-level abstractions that ideally doesn't cost anything at runtime. Not that much boilerplate. A package manager that helps us install things and install things on remote machines. And also using all the computational power we have available. So just one thing I want to say too is Julia is not only numerical computing. Here my example was kind of focused on numerical computing. And I think Julia has evolved a little bit now. So for example, Julia can also be art. So we have just a very narrow selection of packages, but we have the javis.jl, which can do animation type of things. We have, of course, Luxor by Cormullion here to make very nice figures. And I saw this Twitter post saying that I've experienced using Julia for generative art, and it worked very well. And it's also, people use it for games. So here is julgame.jl. It's a game engine in Julia. So to the left there, we have some kind of Pac-Man looking game. In the middle, I don't know, maybe some Zelda looking. And to the right, we have a level editor running in Julia. And of course, there's a lot of web stuff going on. This is just a short selection of packages, but we have the Genie, of course, to make web apps. There's a talk about that. We have Franklin to make websites, and Documenter to do our documentation. And I think Julia is spreading even a little bit further than expected here. This is a Twitter post from someone who was in Egypt. And there was this Julia sign here on this leather trading store. So watch out, we're coming for you next. You don't know where we're going to show up.
All right. So I was tasked with digging through our package servers to pull up some interesting statistics over the last year, just to kind of show how the community has grown and is continuing to expand. So somehow we've managed to grow to where we're serving 170 terabytes of resources every month from the package server network globally, which is not an insignificant amount. There are 2.5 million unique IP addresses served. A new package is registered and served every 7 hours, and a new package version is released on average every 24 minutes. So our community is really, really active, constantly creating these new packages. Clients make 135 requests a second to check for new registries. So every time you say package add or package update, you check for a new registry to find the new versions, and we're getting that 135 times a second. We wanted to pull out a few interesting tidbits looking at the package server data graphs, which you can get from links that are posted on Discord. In this case, we want to give the most improved award to accessors.jl, which went from having only about less than 1,000 downloads a week at the end of JuliaCon last year to this year having over 5,000 downloads a week. So good job, accessors. And if we, instead of looking at per week, we look at per day, when a new version of ordered collections comes out, you end up with 16,000 installs per day, which is just an incredible traffic spike, which I thought was kind of funny to see. You can also see here that people really do use Julia at work, because on the weekends, the installs drop quite a bit. The star history for the base Julia repo continues to skyrocket. We now have over 40,000 stars on the base Julia repository. And for those who are interested, that is when 1.0 was released. And industrial adoption continues. So here we just have kind of a smattering, not even a complete list of the logos of the companies that have publicly talked about their different Julia usage. Of course, we have ASML. For those of you who saw WhatsApp, a little while ago, released a video talking about how they used Julia to prototype the new audio codec, et cetera, et cetera.
So, and those companies are a big part of the community, and also a lot of individuals form this community from around the world. So there's a lot of ways to interact with the community through discourse, if you're looking to be more contributing to folks rather than getting questions answered, and getting questions answered, GitHub issues and pull requests, all those releases coming out, all that activity is also happening in discussions. It's people opening issues, opening pull requests, fixing things. If you have an issue, if you don't understand something, maybe a documentation pull request to a package. And there's Zulip and Slack for more informal communication. And of course, JuliaCon, great way to interact with the community. There's educational resources for getting to know Julia better and to get nice workflows. As more tooling for effective use of Julia comes out, getting that nice Julia experience is evolving. And this Modern Julia Workflows project is an attempt to take people from zero to a basic script and to optimizing code and getting effective systems, making the best use of the existing tooling. So that's a new resource this year. And another new resource this year is this month in Julia World, which is a monthly newsletter. So check that out. And it is posted on Discourse and Slack and Zulip. Yeah. And there's also a lot more resources. These are just the two prominent new resources from this year, but there's a lot of other resources on julialang.org/learning. So a lot of ways to learn from asynchronous communication, as well as the synchronous communication, or closer to synchronous, of these other interaction mechanisms. One huge part of Julia is open source contribution. And something that sets Julia apart from a lot of languages is the transition from writing personal projects to shared code that other people can use is pretty straightforward in Julia. And if you think other people might benefit from your code, feel free to share it. Writing personal code in a package is great because packages provide a whole bunch of infrastructure for like testing, so much tooling to support packages, and the step to publish that package is just a quick registration. And so that transition, combined with the fact that Julia is primarily implemented in Julia, and all the Julia packages are primarily implemented in Julia, makes it really easy to accidentally fix a bug and then give a State of Julia talk a couple years later. So do that. I recommend contributing to packages. It's great. Most folks find package contribution much more effective as a use of time than contributing to the base repository, although love contributing to the base repository too. 1,430 new packages since last JuliaCon. That's a lot of packages. And I think part of the reason that package development can be so productive is that it's very scalable and low risk. If you publish a package and it's like not up to your standards, it's not good, then people won't use it, and that's OK. It doesn't hurt anyone. And in that way, in this big open namespace, we can collaborate and have a lot of people working on a lot of different disparate packages and duplicating effort sometimes and reusing sometimes, and it's lovely to open source your packages. Give us this little gift. Yeah, and this Julia experience, that relies on these packages. That's where CUDA comes from. That's where all the units come from. There's a bit that comes from core Julia, but mostly, if you want to be productive, we need good packages. And so appreciate all those package authors out there. You can do a lot of seemingly internal things in a package. Like Julia syntax, that's a package. PKG, that's a package. Weird. Yeah. Also, of course, contribute to JuliaLang/Julia. Appreciate that, too. So now we're going to talk about some new things that are happening in Julia since last time.
Yeah, so one thing I want to say is that Julia now is better than ever. It's quite common to read that, I tried Julia a couple of years ago. It took quite a long time to plot my thing, and it didn't have the packages I needed. So just as an example here, I did the time to first plot from Julia 1.0 to 1.10. And what I also did, I checked out the registry at that specific release date. So I got like the exact snapshot that someone would have experienced at that point, because quite a lot of this latency work has also taken place in packages. So it's been quite a good improvement. So the time to first plot here, from going from Julia has not been started to it actually showing you a plot, has gone from 16 seconds to 1.4 seconds. And there's been a lot of various latency work. Perhaps the most significant one, which was discussed a little bit last year, is this in 1.9, that the compiled code started being saved to disk. So then it dropped all the way from up here to down here. But even from 1.9 to 1.10, it improved. So the work is ongoing. The number of packages then has increased from over 2,000 to 10,000. So if you try Julia today, you might have a better experience than you did at the 1.0 era. And we also have now a parallel compilation of packages, so actually getting started running code is also much faster. So a little announcement then is that 1.10 will be the new LTS. So 1.6, yeah. So 1.6 is, of course, a great release. It has 7 patch releases with bug fixes. However, for example, we have moved to a new CI system, so it's a little bit hard to make new releases for 1.6. 1.6 does not support, there's a feature compressed registries. Before, you had to unzip all the files in the registry, and especially on Windows, that makes CI pretty slow. 1.6 is starting to be kind of old, especially for a relatively new language. And there's many features that have come since 1.6 that are almost feels like a given now. So, and many authors, they do try to support all the way back to the latest LTS, but I think yeah, it's time to allow them to upgrade now. So this is sort of saying that 1.10 will be the new LTS. Another thing that's happened is that moving out standard libraries from the sysimage. So historically, we had these standard libraries, and all of this was baked into like one big sysimage file. And there was some good things about that. It was quite fast to start with that, and all your standard libraries were immediately loaded. Now the standard libraries, most of them have been moved out, so they're loaded like just like a normal package. So a little bit of a drawback then is that standard libraries are now not free in parentheses to load here. So if I load PKG on 1.10, it's fast, but if I load it on 1.11, it takes a little bit of time. Now, why would we do that? Well, for example, based on this, we have a faster Julia startup time. So there is actually some cost to having to load, for example, a package manager every time you start Julia. If you just want to run your code, then loading a package manager might not be something you want to do. It also allows to upgrade and version standard libraries. We have delimited files and statistics that are trying this now, so I can add statistics, which is a standard library, add some version, and it's going to use that versioned standard library. It's also in some sense a little bit fairer. Like, why should the standard libraries be these in a special position? Let's say sparse arrays is standard libraries. It makes it hard for someone else to write a better sparse arrays library if the standard library is in this special position. There's some, for technical reasons, there's some standard libraries that are still in the sysimage, like linear algebra and random, because they do some type piracy, and sockets, which is used by Julia itself when doing TCP. But there's some thoughts about how maybe to move those out as well. Okay, let's look a little bit at what PKG has improved on. So we have this in 1.11, this new sources section you can put in the project.toml. So before, you used to have to bundle a manifest if you wanted to instantiate a project with unregistered dependencies. But now you can specify a URL or a path for packages in your project file, so you don't have to always carry this manifest around. In 1.12, there's this workspace feature coming up where you can have multiple projects that share a single manifest. So if you have, for example, a monorepo, or you're using many private packages, having all these manifests everywhere can be a bit annoying. Now there can be one manifest, one source of truth. And all these projects refer to that manifest. And then we also have a bit of a work in progress with apps, which is to install command line tunes with the Julia package manager. So right now, let's say you want to start Pluto. You start Julia, you write using Pluto, and then Pluto.run. It would be arguably a bit nicer if you could just install Pluto and then run Pluto in your command line tools. You don't have to do this whole startup procedure.
All right. I'm going to talk a bit about static compilation analysis. Just a quick note on the previous slide. 1.10 is the new LTS. It's been released for a while. 1.11 is going through the release candidate process right now. 1.12 will be released in the future. So last year at JuliaCon, we had some talks about static compilation, how we're going to get away from needing to have a JIT all the time, how we're going to get away from needing to load libllvm all the time. And a lot of the stuff that we talked about was in the future at some point to be worked on. Well, I'm happy to announce that we have 3 talks this year that are talking about different aspects of the progress that has been made in this direction. So Julia is a dynamic but compiled language, right? We write this code that doesn't have strict types assigned, but through type inference, we're able to identify regions of code where we know precisely what the types will be. We call those this kind of static subgraphs of the program. And for those static portions, we're able to highly optimize it, turn it into machine code that knows precisely the kinds of instructions and data types and such that need to be encoded there. So there's been a lot of interest in looking at what would happen if we could make the entire program just one static subgraph. And that's exactly what Julia C aims to do. It tries to provide a mode for Julia to run in that makes the entire thing static so that it can be compiled completely ahead of time. And so if you're interested in that, I suggest you come back here to the main stage to see the new ways to compile Julia talk. There's also a talk by Keno and Shuhei about doing different kinds of static analysis with the Julia compiler. And separately from compilation, a more analysis-focused talk will be with Gabriel and Cody on alloc check, which is a way to use the Julia compiler to check to see if there are any allocations happening in your program, which is a very important thing when you're trying to write high-performance or non-allocating completely code. There have been many improvements to the GPU stack recently. CUDA has an integrated performance profiler, which allows you to not have to exit and reopen with the NVIDIA tools to do simple performance profiling. There's been a lot of work into simplifying application porting, both for the CUDA and AMD stacks, that will work well with unified memory. Improved GC integration to help you bring your memory usage down and have it interact more reliably with Julia's GC. In one API, we now have support for the Aurora supercomputer. Metal has been improved with lots of bug fixes and improvements just all around. And the GPU compiler core package itself now interacts with Julia's precompilation cache, which is going to lead to greatly reduced latency in the future. Tim and Valentine and Catherine have some talks, as you can see on the right there, about these aspects. Just as a quick teaser on the kind of performance improvements we're talking about, in Julia 1.10, which precompiles but does not have a cache, initialization here is taking 70 seconds, whereas in 1.11, with precompilation and the cache, it only takes 12 seconds, and you can see the time steps are also greatly improved due to that precompilation and cached code. I believe the motivating example for this was using a GPU cluster where each node in the cluster was taking like a couple minutes to do the precompilation of these packages, and they're using like weeks of compute time just doing precompilation, whereas now it's brought down to a much more manageable fraction.
So Julia Up is now the official recommended way to install Julia. It's what we showed in the example experience part. It supports installing Julia, which is the primary use of it. And it also has a lot of other nice features. Like it prompts you when there's a new Julia version so that you can update if you'd like. And you can launch as many different versions as you'd like. It's got support for the long-term support, for release, for pre-release, for nightly. Work in progress for for just installing a pull request, a proposed version of Julia. That's in the works coming soon. Highly recommend it. I've been using it for managing Julia versions for a while now. Annotated strings is something that it's raining, lovely. Is something that Timothy's been working on. They allow us to give a first-class representation of metadata attached to strings. So that's going into base, and styled strings, a new standard library, is creating a way of styling them, adding syntax highlighting. And that helps make all sorts of things prettier and makes the user experience or the developer experience of people writing those pretty codes nicer. So that's a useful thing. Mostly it's going to be coming down the pipeline in future versions. There's some REPL improvements coming soon in 1.11 and 1.12, neither of which are released quite yet, but 1.11 is soon, with auto-completion inline suggestions and syntax highlighting in Markdown is going to be 1.12. We've got better error messages ongoing, and we now, when you load a package that hasn't been precompiled, we do parallel precompilation then instead of serial. So that's a thing that might be helpful to some folks. Lowering, so flashback, parsing is now implemented in Julia as of 1.10, I think. And soon, lowering will be as well. And that gives us code provenance. You know where the code, where lowered code comes from. And that's super useful for macros, for escaping, and for better error messages. So see Claire and Tim's talk later. I don't know what room. The public keyword decouples namespacing, that's export, from API, that's which symbols are public or not. And that allows us to more clearly define APIs in packages and in base. And if you ask for the doc string of an internal symbol, you'll now get a warning as of, I think, 1.11. telling you that it's internal. And that allows us to communicate more clearly. And I've got a talk on that later today here. And all these improvements, thanks to our vibrant community. JuliaCon's a celebration of us all, new and old. Thanking the sponsors, the organizers, the attendees. Can't have a conference without attendees. Thank you. Just going to highlight some names, word cloud. These are, for the most part, new contributors to Julia Lang / Julia who haven't committed last year and haven't committed before last JuliaCon. There are going to be a little bit of errors here. Tracking contributions is tricky. But shout out to Timothy for all this styled strings for the formatting better user experience. And shout out to Florian for making pre-compilation improvements and making relocatable precompile files, which is the first step to not requiring local pre-compilation, to being able to serve that. And then you'll never have to wait for pre-compilation again, which would be super cool. Yeah. This is just all the contributors to that repo in the past year since JuliaCon, and this is from all time. There's a lot of people. There's some core ones whose names we probably know, but so many others. It's wild. It's too many to be legible. And even more people contributing to package authors and contributing to packages. So I mean, we shared the highlights of the core language in this talk. The highlights of the package ecosystem are too big to fit in a talk, and so go to all the talks in all the tracks. Yeah, thank you. And now we're going to have a little Q&A. So would the people joining us for the Q&A slither on up to stage?
All right, thanks for the great opening talk. And we have a little bit of time for questions. So I'm sure there will be plenty of questions. If you have one, please raise your hand. And I believe we will throw a mic at you. So we'll see how that works.
Any sort of questions about Julia, the future of Julia, the present?
Now's your chance. You have them all on stage. There's one here in the front. Can we get? We will get you a mic for the stream.
All right, here we go. Ready?
Try to catch it.
All right.
Okay.
Hey, how big is Hello World?
So if you see here on the slide, it's at 890 kilobytes at this point this was taken. So.
Behind you? Yeah.
So there's some cool new features in Julia 1.11 and 1.12. Are any of those going to be like in the compat.jl package for 1.10 for LTS?
Probably not.
Yeah.
A lot of the cool new features can't be backported like that.
That said, I think public and a couple of them are getting like syntax compat. So if you use it, it will do somewhat sensible things.
Yeah, public is supported by compat.jl.
Chris in the back. Yeah, that's going to be a tough throw. Awesome.
Can you speak a little bit to garbage collector improvements and allocation improvements and things going on with improving the timing of code that is allocating?
Here's
Where's the mic? Okay. So working on the garbage collection is a continual improvement. Since the last year, I think last year we got parallel marking, and in the meanwhile we also got parallel sweeping going on, which no, I think we got both. We have concurrent and parallel sweeping. So those are incremental improvements to the garbage collector to make the collections shorter and have them have more work happen while other threads are doing things. And as always, we're working on reducing allocations on packages via optimizations that the compiler can do, aligning allocations that semantically might be there, but the compiler can see that nobody sees the allocations exist, so we can throw them away. And all of these are very iterative things, not necessarily one big thing that changes your code to be non-allocating. You might note small differences here or there.
Is there some way that people can find out if they're allocating or not?
Yes. Me and Cody have a talk about allocheck.jl, which is a tool that helps you reduce your allocations in your code. So go there if you're curious about how to reduce allocations.
The best GC is the one that doesn't have to run.
Yes. Agreed. I have a small question. I know that there's this change on the array interface, and there's this new memory type, and I don't know what that's about. Do you have some words for that?
Oh, no. Oscar? Maybe you can throw it over for the answer?
Oh.
I'm sorry to disappoint all of you with my catching capabilities. Come to main stage at 2:30, I think. Jameson and I are giving a talk on that. But the short answer is, yeah, now array is a first-class Julia object that you can look at the internals of and mess with them. And if you do illegal things, you'll get seg faults. So don't do that.
And there's a new memory type that is like an array, but without all the features. You can't resize it, and it's a little bit simpler. And that's now not a first-class object. Yeah, so you can use this new subtype of abstract array for that.
I wanted to ask about Julia lowering. So the examples here were more about like understanding your code or better error messages. But I wanted to ask, is there also some new capabilities of Julia that could arise from that? Some weird new macro code generation stuff?
Yes, indeed. So do come to the talk. But yes, I've been working on a new macro kind of a new flavor of macros where you can emit like precise error messages from the macro as the macro author, so people will be able to see exactly where in the code. Like it will be just as good as lowering or syntax errors are now. You'll be able to see precisely these characters where the error occurred. And I'm trying to remove ESC. So people who don't like the ESC function who write macros, if you'd like it to go away, then I'll keep working on that.
Yeah.
Yeah, so I guess those are the goodies. But come to the talk on Julia lowering. Actually, the name of the talk is "Dude, Where's My Code?" Come to that tomorrow.
There's one on the right, top right. Tim Holly. We need the mic for the stream, unfortunately.
Mic to Tim Holly.
Thanks, Tim.
Just to add to Claire's answer, the other many good things I think will come from moving lowering into Julia with better provenance, and the sort of applications that might be usable or visible to users are essentially better versions of Cthulhu, better versions of the debugger, and possibly revised could get a sane design and maybe move mostly into Julia itself. So.
Yeah, there's a lot of things that could come from it. I mean, things like stack traces, which tell you precisely where the function call was as well. One day in the future, it's a long process to push that precise provenance information all the way back, like all the way from the parser all the way through the compiler. So we're about a third of the way.
So, loop vectorization has sort of been deprecated with 1.11. Are there any plans to bring some of its functionality back anytime soon?
Is Chris here?
No, Chris. Different Chris.
Yeah, different Chris. But all right.
Can you bring the mic to Chris Wakakis?
Chris can answer.
Yeah, the other Chris I think can answer it. Chris's boss, Chris, can answer it.
Yeah, so we are actually just looking for more people who want to maintain and help grow that stack, right? So loop vectorization did actually get an update for version 1.11. I think that most people might not actually seen there was an update out there, so it actually does run on 1.11. There are 4 known things that need to be done, so that way it'll work on the 1.12. But there is a SciML small grants project, so there is funding for if someone wants to be the next maintainer to help do this. There's an issue list that says exactly how the update needs to happen. We're willing to get new maintainers trained in on this. So yeah, there's nothing really that's required for getting loop vectorization in. It's just more just getting more maintainers in there to help with the maintenance process.
I think long term we will also have to look at adding more vectorization capabilities and vectorization intrinsics and handling modern vectorization styles in the language itself. But that's of course a years-long process to get to a design that everybody agrees with.
Can the static compiler generate for different platforms like Go?
Not yet.
Just behind you.
Thanks. Will there be a time where we can revise everything?
Rewrite?
No.
Revise.
The answer is, the provenance doesn't help with that. The answer is, Tim says no. I'm optimistic, but the answer is probably no.
It depends who answers. Tim will say no. Keno might say yes.
Speaking for Keno, since I'm closer to the mic, yes. Keno has a PR open right now that makes it so that you can revise, or so that you can edit structs. Yeah. Revising them is still a bit out,
but there's still things that you cannot simply revise, and it often also is the question: what does it even mean to redefine the code while it's running?
Yeah, so I think it's never going to be always, but it can get to be much more stuff can be revised.
There's 2 questions in the middle, one in the top, one here. Yeah.
Thank you. Regarding the static compilation, is there any plan to support creating shared libraries so that we can embed it in the existing code? And if so, would it depend on the Julia runtime or not? Or what is the plan?
Yes, there is a plan. Come to our talk. We're going to talk about those things, but yes. About embedding the Julia. So currently, it has this Julia runtime separately. We're working on statically linking all the binaries together so that you have a binary that looks a lot more like one you would get from C or C++ that you wouldn't know that it's a Julia binary. It's just a shared library. And that's on the pipeline, and we're working towards that. So yes, I think the short answer.
With regards to the Julia runtime, it always depends on what you need. If you want to use multi-threading, if you want to use the garbage collection because you're using allocations, then you will need to link against the Julia runtime.
But it will be way smaller than the entire...
So already the Julia runtime is split into the compiler pieces and the real runtime, and I think the real runtime is around 5 to 7 megabytes, whereas the compiler is much larger.
Okay, thank you. Thank you.
In the top middle, second to last row, Mason, I think.
Raise your hand.
Oh, okay, the question has been answered. The last one, then to your left.
No.
Are there any current plans for RISC-V support?
Yes, but we depend on... So getting Julia to build on a new platform requires a stack of things to happen. A couple of them Elliot here has been working on, which is to get the binary builder ecosystem working, because we need to build our dependencies and all of that. We also require LLVM support, which is in progress, and a bunch of things need to happen. A random user, which I cannot remember the name, did get Julia working on a RISC-V with a bunch of patches that they did, and it wasn't super complicated. So I think we're all waiting for a really fast CPU that is capable of running Julia in a good manner, which I don't have access to one, and I think that's pretty much it.
Yeah, so we need development boards or something to run CI on. Ideally, we need like 8 of them to keep up with the constant, deluge of pull requests that people are making against Julia, so we don't accidentally break something. We also need someone who's just very invested in the platform, so that when something breaks on only RISC-V, they're willing to dig in and get to it. You'd be surprised how difficult it is to find that even for like Windows 32-bit, much less RISC-V.
And I would say the same answer holds true for Windows on ARM, since that has been a recent point of questions. We don't have Windows for ARM systems. The compilers aren't ready yet. And it's a huge lift to get a new platform working. So if you care, if you're interested, volunteering is the best way to make sure that that happens.
And we're more than happy to guide these kinds of explorations.
Maybe 2 more questions. One on the right. You already have a mic.
Yeah. So you show that's easy to install Julia and packages anywhere. But we've got clusters and computers without internet access. Do you have any advice on how to avoid my administrator there?
SSH tunnels.
And you can, on many of these systems, you can just straight up copy a depot. So you can install a depot on a machine of that architecture, then just tar it up and move it over.
Yeah, that's also the work that was mentioned earlier from Florian Atteneder, is to make copying depots much easier and simpler.
Okay, cool.
All right, in the interest of time, let's maybe stop here. Thanks for all the questions, but more importantly, thanks for the answering and also the opening talk. Let's thank them again. And before we have our first sponsor talk, I've been told to remind you all that if you have code snippets on your slides, make sure that the font size is big enough, not just for the stage or the room you're in, but also for the online stream. In the past, sometimes it was hard to read on YouTube afterwards. So maybe increase the font size even further on your slides. That goes out to all the speakers.